Now the thing is, we know that if we have different materials, we're going to need a different amount of heat energy to get something to melt, or to boil, or to sublimate. And that's because what we're really saying we have to do, we have to get this molecule away from its neighbor. We have to give it enough kinetic energy that it can pop away. And that's going to depend on how strong the attraction is between them, right? So we need to think through the intermolecular forces. And if we increase any intermolecular forces, we're going to increase melting, freezing, and boiling and condensation points. Well, why is that? Let's think through the process, and let's make it a little more specific than this. Let's say that we're adding, so the amount of energy we have to give something in order to get away from its solid phase neighbor is going to depend on how well it sticks to its neighbor. And the amount of energy needed to get something to boil or condense will also depend on how well it sticks to its neighbor. So if we're going to compare different solutions or different substances, we can think through the intermolecular attractions to decide which one's going to have a higher boiling point, or which one's going to have a higher melting point, or whatever. We can also think through, well, for this substance, for example, water, what will happen if we start adding in salt? Will that increase my boiling point or decrease it? Will that increase my freezing point or decrease it? Those sort of processes. It's all based on how much each of those things are going to attract each other. Now, something else we should point out, though. We're talking about how easy it is to get away from your neighbor. But what if you have external forces keeping you close to your neighbor? And of course, the classic example of that, what if we have our little piston right there? We're pressing down on it. These molecules can't get far away from each other. They're going to stay together. Even if I start heating them up, we're going to keep them a solid and then a liquid for a lot longer, because all these points are going to be pressure and temperature dependent. We don't usually think about it that way, though, because we're used to living at the bottom of a certain atmospheric ocean. We are used to living with 1 atmosphere of atmospheric pressure around us. And so we're not really used to thinking about changing the pressure. We know about the temperature dependence, but we don't think about the pressure part of it very often. But we do have some cases in everyday life, or at least what could be your everyday life soon, where you're going to have to care about those things and where they can do some very nice things for you. Now, if I have more pressure, that means I'm keeping the molecules closer together. That means there's going to be more interaction. That means there's going to be more intermolecular force opportunities for them to hold together. Now, the actual strength is going to stay the same, of course, but they're going to be close enough together that they stick better. That means you're probably going to have a higher melting point and a higher boiling point. Well, let's think through what that might do for us. Suppose we have something like a pressure cooker. We put our food inside of it. Normally, when we have the lid off of it, that's just called a pot. And we're boiling the water, and the water is boiling at 212 Fahrenheit, 100 degrees Celsius. But what we're saying here is, if somehow I put a lid on that system and I let the pressure build up, that means that I should have a higher boiling point. So now, instead of cooking my pasta at, or better yet, my beans at 212 degrees Fahrenheit, now I can be doing it at hotter in Fahrenheit, and let's stay in Celsius, 120 degrees Celsius. That's something that's really going to help me cook my food faster. Before, I was limited to cooking it with 100 degrees Celsius heat. Now I can actually get, temperature. Now I can actually get that temperature up to 120 Celsius, and it's going to cook a lot faster. So that's one of the tricks that we'll commonly use in cooking to let that happen faster. We're exploiting pressure to raise our boiling point and get things to cook faster. Now, there's going to be a spot, though, where we can't really tell the difference between a liquid and gas anymore. Now, I want you to just take a second and try to visualize what we're saying there. Normally, we've got a container. We'll assume that there's a lid on it. We're going to have a meniscus, or a surface at least, of our liquid. Up here, we're going to have gas molecules far enough away that they're not really interacting much. Down here we're going to have things so close together that they are interacting a lot. And I'm trying to get that sketched in by me just tapping a lot of times. There we are. But what happens if we make this lid a piston and we start pushing down? Well, these are going to start getting closer and closer together. And eventually, there's going to be a spot where they're so close together that they start condensing, no matter what the temperature, right? But what if we give it so much heat energy that they're also just ricocheting off of each other so much that the liquid ones don't want to act like liquid anymore? They also want to be in the gas phase. Well, now it's not really going to be a gas or a liquid anymore at all. There's not going to be this surface existing. It's simultaneously a liquid and a gas. And in fact, it becomes something different. When we get above this critical point, it becomes something called supercritical fluid. And a supercritical fluid is a different state of matter.